So they had to fold it up into this kind of complicated origami. And so a large part is figuring out how to fold it up, testing that it unfolded correctly, repeated testing, and there was something like 130 fail points or something during this unfolding mechanism. And so all of us were holding our breath during that process. But if you have the ability to just launch arbitrarily large masses, but it's comparatively compared to JWST, and very large mirrors into space, you could more or less repurpose ground-based mirrors. The Hubble Space Telescope mirror and JWST mirrors are designed to be extremely lightweight, and that increases their cost significantly. They have this kind of honeycomb design on the back to try and minimize the weight. If you don't really care about weight because it's so cheap, then you could just literally grab many of the existing ground-based mirrors across telescopes across the world, 4 meter, 5 meter mirrors, and just pretty much attach them to a chassis and have your own space-based telescope. I think the Breakthrough Foundation, for instance, is an entity that has been interested in doing this sort of thing. And so that raises the prospects of having not just one JWST, but just, JWST is a fantastic resource, but it's split between all of us: cosmologists, star formation astronomers, those of us studying exoplanets, those of us wanting to study the ultra deep fields and the origin of the first galaxies, the expansion of the universe. Everyone has to share this resource, but we could potentially each have one JWST each that is maybe just studying a handful of the brightest exoplanet stars and measuring their atmospheres. This is important because if we talked about this planet Trappist 1e earlier, that planet, if JWST studied it and tried to look for biosignatures, by which I mean oxygen, nitrous oxide, methane, it would take it of order of 200 transits to get even a very marginal, what we call 2.5 sigma detection of those, which basically nobody would read with that. And 100 transits, this thing transits once every 6 days, so you're talking about sort of 4 years of staring at the same stuff with one telescope. There'd be some breaks, but it'd be hard to schedule much else because you have to continuously catch each one of these transits to build up your signal to noise. And so JWST is never going to do that. In principle, technically, JWST could technically have the capability of just about detecting a biosignature on an Earth-like planet around a non-sun-like star, but still, impressively, we have basically the technology to do that, but we simply cannot dedicate all of its time practically to that one resource. And so Starship opens up opportunities like that of mass producing these kinds of telescopes, which will allow us to survey the life in the universe, which of course is one of the grand goals of astronomy.
I wonder if you can speak to the bureaucracy, the political battles, the scientific battles for time on the James Webb Telescope. There must be a fascinating process of scheduling that. All scientists are trying to collaborate, figure out what the most important problems are, and there's an interesting network of interfering scientific experiments probably that just optimize over it.
It's a really difficult process. I don't envy the TAC that are going to have to make this decision. We call it the TAC, the Time Allocation Committee, that make this decision. And I've served in these before, and it's very difficult. Typically for Hubble, we receive at least 10, sometimes 20 times the number of proposals for telescope time versus available telescope time. For JWST, there has been one call already that has gone out. We call it Cycle 1, and that was oversubscribed by, I think, something like 6 to 1, 7 to 1. And the Cycle 2, which has just been announced fairly recently, and the deadline is actually the end of this month, so my team are totally laser focused on writing out proposals right now. That is expected to be much more competitive, probably more comparable to what Hubble saw. And so it's hard.
More competitive than Cycle 1, you said?
Already? More competitive than the first cycle. So I said the first cycle of James Webb was about 6 to 1, and this is probably more like 20 to 1. I would expect.
So these are all proposals by scientists and so on. It's not like you can schedule at any time, because if you look at the transit times,
you have a time critical element.
Yes, time critical element, and they're conflicting in non-obvious ways because the frequency is different, the duration is different. It's probably computational needs. Yeah, they're different. The type of sensors, the direction pointing, all that.
Yeah, it's hard. And there are certain programs like doing a deep field study where you just more or less point a telescope, and that's pretty open. You're just accumulating photons. So you can just point at the the sky whenever the telescope's not doing anything else, and just get to your month, let's say a month of integration time is your goal over the lifetime of JVST. So that's maybe a little bit easier to schedule. It's harder, especially for us looking at cool worlds, because as I said earlier, these planets transit very infrequently. So we have to wait, looking at the Earth transiting the Sun, and alien watching us. They would only get one opportunity per year to do that observation. The transit lasts for about 12 hours. And so if they don't get that time, it's hard. That's it. If it conflicted with another proposal that wants to use another time critical element, it's much easier for planets like these hot planets with ozone planets, because they transit so frequently. There's maybe 100 opportunities, and so then the TAC can say, okay, they want 10 transits. There's 100 opportunities here. It's easier for us to give them time. We're almost in the worst case scenario. We're proposing to approximate around 2 cool planets, and so we really only have one bite of the cherry for each one. And so our sales pitch has been that these are extremely precious events, and more importantly, JWST is the only telescope, the only machine humanity has ever constructed, which is capable of finding moons akin to the moons in our solar system. Kepler can't do it, Hubble can't do it. JWST is the first one. And so there is a new window to the universe, because we know these moons exist. They're all over the place in the solar system. You have the moon, you have Io, Callisto, Europa, Ganymede, Titan. Lots of moons are fairly similar size, with 30% the size of the Earth. And this telescope is the first one that can find them. And so we're very excited about the profound implications of ultimately solving this journey we're on in astronomy, which is to understand our uniqueness. We want to understand how common is the solar system. Are we the architecture that frequently emerges naturally, or is there something special about what happened here?
I think this is not the worst case. The best case is obvious. It's super rare. So you have to I love scheduling from a computer science perspective. That's my background. So algorithmically, to solve a scheduling problem, I will schedule the rarest things first. And obviously, this is the JWST is the first thing that can actually detect a cool world. This is a big new thing. You can show off that new thing. It happens rarely. Schedule it first. Perfect.
You should be in the TAC.
Yeah, I like that. I will. I'll file my application after going. This part of me is the OCD part of me is the computational aspect. I love scheduling computing device, because you have that kind of scheduling on supercomputers. That scheduling problem is fascinating. How you prioritize computation, how you prioritize science, data collection, sample collection, all that kind of stuff. It's actually kind of fascinating, because data, in ways you expect and don't expect, will unlock a lot of solutions. So fascinating mysteries. So collecting the data and doing so in a way that maximizes the possibility of discovery is really interesting. Like from a computational perspective.
I agree. There's a real satisfaction extracting the maximum science per time
exactly
out of your telescope, and that's the TAC's job. But the TAC are not machines; they're not a piece of computer code. They will make their selections based off human judgment, and a lot of the telescopes, certainly within the field of exoplanets, because it's different fields of astronomy, but within the field of exoplanets, I think a good expectation is that most of the telescope time that JWST have will go towards atmospheric retrieval, which is subaloots really detecting molecules in atmospheres, not biosignatures, because that's really not designed to do that. It's pushing JWST probably too far to expect it to do that. But it could detect, for example, a carbon dioxide-rich atmosphere of TRAPPIST-1e. That's not a biosignature, but you could prove it's like a Venus in that case, or maybe like a Mars in that case. Like both those have carbon dioxide-rich atmospheres. It doesn't prove or disprove the existence of life either way, but it is our first characterization of the nature of those atmospheres. Maybe we can tell the pressure level and the temperature of those atmospheres. So that's very exciting. But we are competing with that, and I think that science is completely mind-blowing, fantastic. We have a completely different objective, which is in our case to try and look for the first evidence of these small moons around these planets, potentially even moons which could be habitable, of course. So I think it's a very exciting goal, but ATTAC has to make a human judgment essentially about which science are they most excited by, which one has the highest promise of return, the highest chance of return. And so that's hard, because if you look at a planetary atmosphere, But you know, most of the time, it has an atmosphere already. And so there's almost a guaranteed success that you're going to learn something about the atmosphere by the point of doing this to your deck. Whereas in our case, there's a harder sell. We are looking for something that we do not know for sure exists yet or not. And so we are pushing the telescope to do something which is inherently more risky.
Yeah, but the existence it's shown already gives a deep lesson about what's out there in the universe. That means that other stars have similar types of variety as we have in our solar system. They have an Io, they have Europa, and so on, which means like there's a lot of possibility for icy planets, for water, for planets that enable planets. I mean, that's super exciting because that means everywhere through our galaxy and beyond, there is just innumerable possibilities for creatures.
I mean,
Yeah,
NASA has been on this quest for a long time. It's sometimes called Beta Earth. It's the frequency of Earth-like, usually there's planets in the universe. How common are planets similar to our Earth in terms of ultimately we'd like to know everything about these planets in terms of the amount of water they have, how much atmosphere they have, but for now it's kind of focused just on the size and the distance from the star essentially. How often do you get similar conditions to that? That was Kepler's primary mission, and it really just kind of flirted with the answer, didn't quite get to a definitive answer. But I always say that if we're looking, if that's our primary goal, to look for Earth-like, I would say, worlds, then moons has to be a part of that, because we know that Earth-like, from the Kepler data, the preliminary result is that Earth-like planets around sun-like stars is not an inevitable outcome. It seems to be something like a 1 to 10% outcome, so it's not particularly inevitable that happens. But we do often see about half of all sun-like stars have either a mini Neptune, a Neptune, or a Jupiter in the outer zone of those stars. That's a very, very common occurrence that we see. Yet we have no idea how often they have moons around them, which could also be habitable. And so it may very well be, if even 1 in 5 of them has an Earth-like moon or even a Mars-like moon around them, then there would be more habitable real estate in terms of exomoons than exoplanets.
Because essentially 2x, 3x, 5x, maybe 10x the number of habitable worlds out there in the universe at our current estimate, like the Drake equation.
Absolutely.
So this is one way to increase the confidence and increase the value of that parameter.
And just know where to look. I mean, we would like to know where should we listen for techno signatures, where should we be looking for biosignatures, and not only that, but what role does the moon have in terms of its influence on the planet? We talked about these directly imaged telescopes earlier, these missions that want to take a photo, to quote Carl Sagan, the pale blue dot of our planet, the pale blue dot of an exoplanet. And that's the dream, to one day capture that. But as impressive as the resolution is that we are planning and conspiring to design for future generation telescopes to achieve that, even those telescopes will not have the capability of resolving the Earth and the Moon within that. It'll be a pale blue dot pixel, but the Moon's grayness will be intermixed with that pixel. And so this is a big problem, because one of the ways that we are claiming to look for life in the universe is a chemical disequilibrium. So you see two molecules that just shouldn't be there. They normally react with each other. Or even one molecule that's just too reactive to be hanging around the atmosphere by itself. So if you had oxygen and methane hanging out together, those would normally react fairly easily. And so if we detected those two molecules in the pale blue dot spectrum, you'd be like, okay, you have evidence for life. Something's metabolizing on this planet. However, the challenge is, what if that moon was Titan? Titan has a methane-rich atmosphere. And what if the pale blue dot was in fact a planet devoid of life, but it had oxygen because of water undergoing this photolysis reaction, splitting into oxygen and hydrogen separately. So then you have all of the hallmarks of what we would think is life. But all along we were tricked. It was just a moon that was deceiving. And so we're never going to outplay and really understand or complete this quest of looking for life, biosignatures in the universe, unless we have a deep knowledge of the prevalence and role that moons have. They may even affect the habitability of the planets themselves. ring moon freakishly large. By mass ratio, it's the largest moon in the solar system. It's a 1% mass moon. Look at Jupiter's moons are 10 to the power minus 4, much smaller. And so our own moon seems to stabilize the obliquity of our planet. It gives rise to tides, especially early on when the moon was closer, those tides would become entire continents. And those rock pools that would have been scattered across the entire plateau may have been the origin of life on that planet. The moon-forming impact may have stripped a significant fraction of the lithosphere off the Earth, which without it, plate tectonics may not have been possible. We got a stagnant lid because there's just too much lithosphere stuck on the top of the planet. And so there are speculative reasons, but intriguing reasons as to why a large moon may be not just important, but central to the question of having the conditions necessary for life. So moons can be habitable in their own right, but they can also play a significant influence on the habitability of the planets they orbit. And further, they will surely interfere with our attempts to detect life remotely from afar.
So, taking a tangent on a tangent, you've written about binary planets. What's and that they're surprisingly common, or they might be surprisingly common. What's the difference between a large moon and a binary planet? What are binary planets? But what's interesting to say here about giant rocks flying through space and orbiting each other?
I think it's interesting that binary objects is a very common in the universe. Binary stars are everywhere, but the majority of stars seem to live in binary systems. When we look at the outer edges of the solar system, we see binary Kuiper belt objects all the time, asteroids basically bound to one another. Pluto Charon is kind of an example of that. It's a 10% mass ratio system. It almost is, by many definitions, a binary planet, but now it's a dwarf planet, so yeah, I like it. Yeah, call that now. But we know that the universe likes to make things in pairs.
So you're saying our sun is an incel. it's looking. So most things are dating for relationships, and ours is alone.
It's not a complete freak of the universe to be alone, but it is. It's more common for sun-like stars. If you count up all the sun-like stars in the universe, about half of the sun-like star systems are in binary or trinary systems, and the other half are single. But because those binaries are 2 or 3 stars, then cumulatively, maybe like a third of all sun-like stars are single.
I'm trying hard to not anthropomorphize the room. I've met those folks also. So, is there something interesting to learn about the habitability, how that affects the probability of habitable worlds when they kind of couple up like that in different ways?
Well, it depends when we're talking about the stars and planets. Certainly, if stars couple up, that has a big influence on the habitability. Of course, this is very famous from Star Wars. Tatooine in Star Wars is a binary star system. You have Luke Skywalker looking at the sunset and seeing 2 stars come down. And for years, we thought that was purely a product of George Lucas's incredibly busy mind, and we didn't think that planets would exist around binary star systems. It seems like too tumultuous an environment for a quiescent planetary disk, circumstellar disk, to form planets from. And yet, one of the astounding discoveries from Kepler was that these appear to be quite common. In fact, as far as we can tell, they're just as common around binary stars as single stars. The only caveat to that is that you don't get planets close in binary stars. They have like a clearance region on the inside where planets, maybe they form there, but they don't last. They're dynamically unstable in that zone. But once you get out to about the distance that the Earth orbits the Sun, or even a little bit closer in, you start to find planets emerging. And so that's the right distance for liquid water, so the right distance for potential life on those planets. And so there may very well be plenty of habitable planets around binary stars. Binary planets is a little bit different. Binary planets, I don't think we have any serious connection of planet binarity to habitability. Certainly when we've estimated it, that wasn't right, that this is somehow the solution to life in the universe or anything. It was really just like all good science questions, a curiosity driven.
Wasn't the dynamic the legit orbiting each other as they orbit the star?
So the formation mechanism proposed here, because it is very difficult to form 2 protoplanets close to each other like this. They were generally merged disk, and so that's why we look at single planets. But you could have something like Jupiter and Saturn form at separate distances. They could dynamically be scattered in towards one another and basically not quite collide, but have a very close-on encounter. Now, because tidal forces increase dramatically as the distance decreases between two objects, the tides can actually dissipate the kinetic energy and bring them bound into one another. So that seems, when when you first hear that, you think that seems fairly contrived, that you'd have the conditions just right to get these tides to cause a capture. But numerical simulations have shown that about 10% of planet-planet encounters are shown to produce something like planets, which is a startling prediction. And so that seems at odds with, naively, the exoplanet catalogue, which we know of so far no binary planets. And we propose one of the resolutions to this might be that the binary planets are just incredibly difficult to detect, which is also counterintuitive, because remember how they form is through this tidal mechanism. And so they form extremely close to each other. So the distance that Io is away from Jupiter, just a few planetary radii, they're almost touching one another, and they're just tightly locked, facing each other for eternity. And so in that configuration, as it transits across the star, it kind of looks like you can't really resolve these two planets. It just looks like one planet to you that's going across the star. The temporal resolution of the data is rarely good enough to distinguish that. And so you see one transit, but in fact it's two planets very close together, which are transiting at once. And so, yeah, we wrote a paper just recently where we developed some techniques to try and get around this problem, and hopefully provide a tool where we could finally look for these planets.
The problem detection.
Yeah, that was our focus. Was how do you get around this emerging problem? So whether they're out there or not, we don't know. We're planning to do a search for them, but it remains an open question. And I think just one of those fun astrophysics curiosities questions, whether binary planets exist in the universe. Because then you have binary Earth, you can have binary Neptune, all sorts of wild stuff that would float the sci-fi imagination.
I wonder what the physics of binary planet feels like. It might be trivial. I have to think about that. I wonder if there's some interesting dynamics. Like, you feel multiple, or would gravity feel different on different parts of the surface of the sphere when there's another large sphere?
I would think that the force would be fairly similar, because the shape of the object would deform to a flat geopotential, essentially a uniform geopotential, but it would lead to a distorted shape of the two objects. I think they'd become ellipsoids facing one another. So it would be pretty wild when people like flat Earth or spherical Earth, you fly from space and see a football-shaped Earth.
Finally, there's proof, and I wonder how difficult it is to travel from one to the other, because you have to overcome the no, it might be kind of easy.
Yeah, I mean, they're so close to each other that helps. And I think the most critical factor would be how massive is the planet. That's always, I mean, one of the challenges with escaping planets, there was a fun paper one of my colleagues wrote that suggested that super Earth planets may be inescapable. If you're a civilization that was born on a super Earth, the surface gravity is so high that the chemical potential energy of hydrogen or methane, whatever fuel you're using, simply is at odds with the gravity of the planet itself. And so you would, our current rockets, I'm not sure the fraction, maybe like 90% of the rocket is fuel or something by mass. These things would have to be like the size of the Giza pyramids of fuel with just a tiny tip on the top in order just to escape that planet's atmosphere. And so it has been argued that if you live on a super Earth, you may be forced to live there forever. There may be no escape unless you invent a space elevator or something. But then, how do you even build the infrastructure in space to do something like that in the absence of a successful rocket program? And so the more and more we look at our Earth and think about the sorts of problems we're facing, the more you see things about the Earth which make it ideally suited in so many regards. It's almost spooky, right? That we don't only live on a planet which has the right conditions for life, for intelligent life, for sustained fossil fuel industry just happens to be in the ground. We have plenty of fossil fuels to get our industrial revolution going. But also the chemical energy contained within those fossil fuels, like hydrogen, other fuels, is sufficient that we have the ability to escape our planetary atmosphere and planetary gravity, to have a space program. And we also happen to have a celestial body which is just within reach, the moon, which does also necessarily have to be true. Were the moon not there, what effect would that have had on aspirations of a space program? Would there have ever been space race to Mars or to Venus? That's a much harder, certainly for a human program, that seems almost impossible with major technology to imagine that was going to fruition.
It's almost as if somebody constructed a set of challenging obstacles before us, challenging problems to solve. They're challenging, but they're doable. And there's a sequence of them. Gravity is very difficult to overcome, but we have, given the size of Earth, it's not so bad that we can still actually construct propulsion systems that can escape it.
Yeah. And the same with climate change, perhaps. I mean, climate change is the next major problem facing our civilization, but we know it is technically surmountable. It does seem sometimes like there has been a series of challenges laid out to progress us towards a mature civilization that could one day perhaps expand to the stars.
I'm a little more concerned about nuclear weapons, AI, natural or artificial pandemics. But yes,
there's plenty of milestones that we need to cross, and we can argue about the severity of each one, but there is no doubt that we live in a world that has serious challenges that are pushing our intellects and our will to the limit of whether we're really ready to progress to the next stage of our development.
So thank you for taking the tangent, and there'll be a minute more. But can we step back to Kepler 1625b? What is it? And you've talked about this kind of journey, this effort to discover exomoons, so moons out there, or small, cool objects out there. Where does that effort stand, and what is Kepler 1625?
Yeah, I've been searching for most of my professional career, and I think a lot of my colleagues think I'm kind of crazy to still be doing it. After 5 years of not finding anything, I think most people would probably try doing something else. I even had people say to me, they said, professors, I remember a cocktail party took me to the side, an MIT professor, and said, you should just look at hot Jupiter. We can go papers, there's so easy to find. And I was like, yeah, but hot Jupiter's just, they're not interesting to me. I want to do something that I feel intellectually pushes me to the edge, and there's maybe a contribution that no one else could do, but maybe is not certainly the thing that anybody could do. I don't want to just be the first to something for the sake of being first. I want to do something that feels like a meaningful intellectual contribution to our society. And so this exomoon problem has been haunting me for years to try and solve this. Now, as I said, we looked for years and years using Kepler, and the closest we ever got was just a hint that there's one star, Kepler 1625, has a Jupiter-like planet in orbit of it. And that Jupiter-like planet is on a 287-day period, so it's almost the same distance as the Earth-like sun for Jupiter. So that was already unusual. I don't think people realize that Jupiter-like planets are quite rare in the universe. Certainly, mini Neptunes and Neptunes are extremely common, but Jupiter's only about 10% of sun-like stars have Jupiters around them, as far as we can tell.
When you say Jupiter, which aspect of Jupiter?
In terms of its mass and its center axis. So anything beyond about half an AU, so half the distance of the Earth and the Sun, and something of order of a tenth of a Jupiter mass, that's the mass of Saturn, up to say 10 Jupiter masses, which is basically where you start to get to brown dwarfs. Those types of objects appear to be somewhat unusual. Most solar systems do not have Jupiters, which is really interesting because Jupiter, again, like the Moon, seems to have been a pivotal character in the story of the development of our solar system, perhaps especially having a large influence in the development of the bombardment and the rate of asteroid impacts that we see and things like this. Anyway, to come back to 1625, this Jupiter-like planet had a hint of something in the data. But what I mean by that is when we looked at the transit, we got the familiar decrease in light that we always see when a planet travels in front of a star. But we saw something extra. Just on the edges, we saw some extra dips around the outside. It was right at the hairy edge of detectability. We didn't believe it because I think one of the challenges of looking for something for 10 years is that you become your own greatest skeptic. And no matter what you're shown, you're always thinking, it's like falling in love so many times and it not working out. You convince yourself it's never going to be it's never going to happen. Not for me. You know, this isn't going to happen. And so I saw that, and I didn't really believe it, because I didn't dare let myself believe it. But being a good scientist, we knew we had an obligation to publish it, to talk about the result, and to follow it up, and to try and resolve what was going on. So we asked for Hubble Space Telescope time, which was awarded in that case, and we were one of those lucky 20 that got telescope time. And we stared at it for about 40 hours continuously. And to provide some context, the dip that we saw in the Kepler data corresponded to a Neptune-sized moon around a Jupiter-sized planet, which was another reason why I was skeptical. I think that we didn't have that in the solar system. That seems so strange. And then when we got the Hubble data, it seemed to confirm exactly that. There was two really striking pieces of evidence in the data that suggested this moon was there. Another was a fairly clear second dip in light, pretty clearly resolved by Hubble, just by the 5 sigma detection. And on top of that, we could see the planet didn't transit when it should have done. It actually transited earlier than we expected it to, by about 20 minutes or so. And so that's a hallmark of a gravitational attraction between the planet and the moon. We actually expected that. You can also expect that if the moon transits after the planet, then the planet should come in earlier than expected, because the barycenter, the center of mass, lives between the two of them, kind of like on a balancing arm between them. And so we saw that as well. So the phase thing which matched up. The mass of the moon was measured to be Neptune mass, and the size of the moon was measured to be Neptune radius. And so everything just really lined up, and we spent months and months trying to kill it. This is my strategy for anything interesting. We just try to throw the kitchen sink at it and say, we must be tricked by something. And so we tried looking at the centroid motion of the telescope, at the different wavelength channels of the pixel level information. And no matter what we did, we just couldn't get rid of it. And so we submitted to Science. And I think at the time, Science, which was one of the top journals, said to us, would you mind calling your paper Discovery of an Exomoon? And I had to push back, and we said, no, we're not calling it that. Even despite everything we've done, we're not calling it discovery, we're calling it evidence for an exomoon. Because for me, I'd want to see this repeat 2 times, 3 times, 4 times before I really would bet my house that this is the real. I mean, and I do worry, as I said, that perhaps that's my own skepticism, self-skepticism going too far. But I think it was the right decision, and since that paper came out, there has been continuous interest in the subject. Another team independently analysed that star and recovered actually pretty much exactly the same results as us, the same dip, the same wobble of the planet. And a third team looked at it and actually got something different. They saw the dip was diminished compared to what we saw. They saw a little hint of a dip, but not as pronounced as what we saw. And they saw the wobble as well. So there's been a little bit of tension about analysing the reduction of the Hubble data. And so the only way, in my mind, to resolve this is just to look again. We actually did propose to Hubble straight after that. And we said, look, if our model is right, if the moon is there, it came in late last time. It transited after the planet. Because of the orbit, we can calculate that it should transit before the planet next time. If it's not there, it doesn't transit before. And even if we see a dip afterwards, we know that's not our moon. It's obviously some instrumental effect of the data. We had a causal prediction as to where the moon should be. And so I was really excited about that, but we didn't get the telescope time. Unfortunately, if you go further into the future, we no longer have the predictive capability, because it's like predicting the weather. You might be able to predict the weather next week to some level of accuracy, but predicting the weather next year becomes incredibly hard. The uncertainties just grow and compound as you go forward into the future more and more.
But how are you able to know where the moon will be positioned? So you're able to tell the orbiting like geometry and frequency?
Yeah, so from the basically from the wobbles of the planet itself, that tells us the orbital motion of the moon, the reflex motion of the moon. But
Isn't it just an estimate where, like, I'm concerned about you making a strong prediction here, because like if you don't get the moon where the moon needs on the next time around, if you did get Hubble cloud, couldn't that mean something else if you didn't see that? Like, because you said it would be an instrumental. I feel the strong urge to disprove your, which is a really good narrative. It's a good way to science, but like this is such a noisy signal, right? Or blurry signal, maybe. Low resolution signal.
Yeah, I mean it's a 5 sigma signal. So that's at the slightly uncomfortable edge. I mean, it's often said that for any detection of a first new phenomenon, you really want like a 20, 25 sigma detection, and then there's just no doubt that what you're seeing is real. This was at that edge. I mean, I guess it's comparable to the Higgs boson, but the Higgs boson was slightly different because there was so much theoretical impetus to expect a signal at that precise location. A Neptune-sized moon was not predicted by anyone. There was no papers you can find that expect Neptune-sized moons or Jupiter-sized planets. So I think we were inherently skeptical about its reality for that reason. But this is science in action, and when we fit the wobbles, we fit the dips, and we have this 3D geometric model for the motion of the orbit, and projecting that forward, we found that about 80% of our projections led to the moon to be before. So it's not 100%. There was maybe 20% of the cases it was over here. But to me, that was a hard enough projection that we felt confident that we could refute it, which was what I really wanted. I wanted refutable. It's the basis of science, a falsifiable hypothesis. How can you make progress in science if you don't have a falsifiable, testable hypothesis? And so that was the beauty of this particular case.
So there's a numerical simulation of the moon. If it's the data that we observed, and you can now make predictions based on that simulation.
Yeah.
That's so cool.
Okay, it's fun. These are like little solar systems that we can simulate on the imagine their motions, but we are pushing things to the very limits of what's possible, and that's a double-edged sword. It's both incredibly exciting intellectually, but you're always risking to some degree the pushing too far.
So I'd like to ask you about the recent paper you co-authored, an exomoon survey of 70 cool giant exoplanets, and the new candidate Kepler 1708 BI.
I'd say there's like 3 or 4 candidates at this point, of which we have published 2 of them. And to me, 2 are quite compelling and deserve follow-up observations. And so to get a confirmed detection, at least in that case, we need to see repeat for sure. One of the problems with some of the other methods that have been proposed is that you don't get that repeatability. So, for instance, an example of a technique that would lack that would be gravitational micromixing. So it is possible with a new telescope coming up in the future, called the Rabbi Space Telescope, which is basically a repurposed by satellite that's the size of the Hubble mirror going up into space. It will stare at millions of stars simultaneously, and it will look to see, instead of whether any of those stars get dimmer for a short amount of time, which will be a transit, it'll look for the opposite. It'll look to see if they can get brighter. And that brightness increase is caused by another planetary system passing in front, and then gravitation and lensing around it causes brightening. And so this is a method of discovering an entire solar system, but only for a glimpse. You just get a short glimpse of it passing like a ship sailing through the night, just that one photo of it. Now the problem with that is that it's very difficult. The physics of gravitational lensing are not surprisingly quite complicated, and so there's many possible solutions. So you might have a solution which is this could be a red dwarf star with a Jupiter-like planet around it. That's one solution. But another solution is it's a free-floating planet, a rogue planet like Jupiter, with an Earth-like thing around it. And those 2 solutions are almost indistinguishable. Now, ideally, we would be able to repeat the observation. We'd be able to go back and see what if the moon really is there, then we can predict its mass, predict its motion, expect it to be maybe over here next time or something. With microlensing, it's a one snapshot event. And so for me, it's intriguing as a way of revealing something like this in this population. But I always come back to transits because it's the only method we really have that's absolutely repeatable, that will be able to come back and prove to everyone that, look, on the 17th of October, the moon will be over here, or the moon will look like this, and we can actually capture that image. And that's what we see with, of course, the exoplanets. So we want to get to that same point of full confidence, full confirmation, the slammed detection of these exomoons. But it's been a hell of a journey to try and push the field into that direction. And
is there some resistance to the transit method?
Not just the transit, I just said to exoplanets. So the transit method is by far the most popular method for looking for exoplanets. But yeah, as I've alluded to, exomoons is kind of a niche topic within the discipline of exoplanets, and that's largely because there are people I think are waiting for those slam dunks. And it was like if you go back to the first exoplanet discovery that was made in 1995 by Michel Mayor and Didier Queloz, I think it's true at the time that they were seen as mavericks, that the idea of looking for planets around stars was considered fringe science. And I'm sure many colleagues told them, why don't we do something more safe, like study eclipsing stars? Two binary star systems, we know those exist, so why are you wasting your time looking for planets? You're going to get this alien moniker or something. You'll be seen as a fringe maverick scientist. And so I think it was quite difficult for those early planet hunters to get legitimacy and be taken seriously. And so very few people risked their careers to do it, except for those that were either emboldened to try or had maybe the career, maybe like a tenure or something, so they didn't have to necessarily worry about the implications of failure. And so once that happened, once they made the first discoveries, overnight, everyone and their dog was getting into exoplanets, and all of a sudden the whole astronomy community shifted, and huge numbers of people that were once upon a time studying eclipsing binaries changed to becoming exoplanet scientists. And so that was the first wave of exoplanet scientists. We're now in a kind of a second wave, or maybe a third wave, where people like me, to some degree, kind of grew up with the idea of exoplanets as being normal. I was 11 years old, I guess, when the first exoplanet was discovered, and so to me it was a fairly normal idea to grow up with. And so we've been trained in exoplanets from the very beginning. And so that brings a different perspective to those who have maybe transitioned from a different career path. And so I suspect with exomoons and probably technosignatures, astrobiology, many of the topics which I've seen at the fringes of what's possible, they will all open up into becoming mainstream one day. But there's a lot of people who are just waiting for that assuredness that there is a secure career net ahead of them before they connect.
Yeah, it does seem to be that exomoons open wider, or open for the first time, the door to aliens. Just more seriously academically studying, all right, let's look at like alien worlds. So I think it's still pretty fringe to talk about alien life, even on like at Mars and the moon and so on. You kind of like, it would be nice, but imagine the first time to discover a living organism. That's going to change. Then everybody will look like an idiot for not focusing everything on this. Because the possibility of the things it's possible it might be super boring. It might be very boring bacteria, but even the existence of life elsewhere, that changes everything. That means life is everywhere.
Yeah. If you knew now that in 5 years, 10 years, the first life would be discovered elsewhere, you knew that in advance, it would surely affect the way you approach your entire career. Especially someone junior in astronomy, you would surely be like, well, this is clearly going to be the direction I have to dedicate my classes and my training and my education towards that direction.
All the new textbooks, all the written, and I think there's a lot of value to hedging, like allocating some of the time to that possibility. Because the kind of discoveries we might get in the next few decades, it feels like we're on the verge of getting a lot of really good data and having better and better tools that can process that data. So there's just going to be a continuous increase of the kind of discoveries that will open. But a slam dunk, that's hard to come by.
Yeah, I think a lot of us are anticipating, we're already seeing it to some degree with Venus and the philosophy incident. But we've seen before with Bill Clinton and the White House North announcing life on Mars. There are inevitably going to be spurious claims, or at least claims which are ambiguous to some degree. There will be, for sure, a high-profile journal like Nature or Science that will one day publish a paper saying biosignature discovered or something like that on TRAPPIST-1 or some other planet, and then there will be years of back and forth in the literature, and that might seem frustrating, but that's how science works. That's the mechanism of science at play, of people scrutinizing the results to intense skepticism, and it's like a crucible you burn away all irrelevances until whatever is left is the truth, and so you're left with this product, which is that okay, we either believe or don't believe the right thing which is there. So there's inevitably going to be a lot of controversy and debate and argument about it. We just have to anticipate that, and so I think you have to basically have a thick skin to some degree academically to dive into that world, and you're seeing that with phosphine. It's been it's been uncomfortable to watch from the outside, the kind of dialogue that some of the scientists have been having with each other about that, because
To get a little aggressive.
yeah, and you can understand why, because
Jealousy? I don't know. That's me saying, not you. That's me talking.
I'm sure there's some envy and jealousy involved on the behalf of those who are not part of the original discovery. But there's also, in any case, just to leave the particular people involved in Venus alone, in any case of making a claim of that magnitude, especially life, because life is pretty much one of the biggest discoveries of all time that you can imagine scientifically. You can see, and I'm so conscious of this in myself when I get close to, as I said, even much smaller goals, setting an exomoon, the ego creeping. And so, as a scientist, we have to be so guarded against our own egos. You see the lights in your eyes of the Nobel Prize, or the fame, fortune, and remember the history books. And we all grew up in our training learning about Newton and Einstein, these giants of the field, Feynman, Maxwell, and you get the idea of these individual contributions which get immortalized for all time, and that's seductive. It's why many of us with the skill set to go into maybe banking instead decided, actually, there's something about the idea of being immortalized and contributing towards society in a permanent way that is more attractive than the financial reward of applying my skills elsewhere. So to some degree, that ego can be a benefit because it brings in skills for people into our field who might otherwise be tempted by money elsewhere. But on the other hand, the closer you get towards when you start with that Nobel Prize in your eyes, when you think you're on the verge of seeing something, you can lose objectivity. A very famous example of this is Barnard's star. There was a planet claimed there by Peter van der Kamp, I think it was in 1968, 69. And at the time, it would have been the first ever exoplanet ever claimed. And he felt assured that this planet was there. He was actually using the wobbling star method, but using the positions of the stars to see them to claim this exoplanet. It turned out that this planet was not there. Subsequent analyses by both dynamicists, theorists, and those looking at the instrumental data established fairly unanimously that there was no way this planet was really there. But Peter van der Kamp insisted it was there, despite overwhelming evidence that was accruing against him. And even to the day he died, which was, I think, in the early 90s, he was still insisting this planet was there, even when we were starting to make the first genuine exoplanet discoveries. And even at that point, I think Hubble had even looked at that star and had totally ruled out any possibility of what he was talking about. And so that's a problem. How do you get to a point as a scientist where you just can't accept anything that comes otherwise, because it starts out with the dream of fame, and then it ends in a stubborn refusal to ever back down.
Of course, the flip side of that, sometimes you need that to have the strength to carry a belief against the entire scientific community that resists your belief. So it's a double-edged sword.
That can happen, but I guess the distinction here is evidence.
Yes.
So in this case, the evidence was so overwhelming. It wasn't really a matter of interpretation. It was you had to you'd observe this star with the same star, but with maybe 10, even 100 times greater precision for prolonged, much longer periods of time, and there was just no doubt at this point this planet was a mirage. And so that's why you have to be very careful. I always say, don't ever name, my wife and my daughter, name this planet after me that you discover. And I can't ever name a planet after you, because I won't be objective anymore. How could I ever turn around to you and say that planet wasn't real, that I named after you?
So you hear somebody that talks about it, and it's clear in your eyes and your way of being, and you love the process of discovery, that joy and the magic of just, uh, you know, seeing something, new observation, a new idea, right? But I guess the point is when you have that great feeling, is to then switch on the skepticism, like to start like testing. What does this actually mean? Is this real? What are the possible different interpretations that could make this a lot less grand than I first imagined? So both have the wonder and the skepticism all in one way.
Yeah, I think generally the more I want something to be true, the more I inherently doubt it. And I think that just comes from, I grew up with a religious family and was just sort of indoctrinated to some degree, like many children are, that okay, this is normal, that there's a God and this is the way the world is. God created the earth. And then as I became more, well read and literate of what was happening more scientifically, I started to doubt. And it really just struck me that the hardest thing to let go of when you do decide not to be religious anymore, and it's not really like a light bulb moment, but it just kind of happens over sort of 11 to 13, I think for me it was happening. But it's that sadness of letting go of this beautiful dream which you had in your mind of eternal life, for behaving yourself on earth. You would have this beautiful heaven you could go to and live forever, and that's very attractive. And for me personally, that was one of the things that pulled me against it. Was this? It's actually good to be true, and it's very convenient that this could be so. And I have no evidence directly in terms of scientific sense to support this hypothesis. And it just became really difficult to reconcile my growth as a scientist. And I know some people find that reconciliation. I have not. Maybe I will one day. But as a general guiding principle, which I think I obtained from that experience, was that I have to be extremely guarded about what I want to be true, because it's going to sway me to say things which are not true if I'm not careful. And that's not what we're trained to do as scientists.
So you felt from a religious perspective that there was a little bit of a gravitational field in terms of your opinions, like it was affecting how you could be as a scientist. Like as a scientific thinker, obviously you were really young.
Yeah, I think I think that's true. That whenever there's something you want to be true, it's the ultimate seduction intellectually. And I worry about this a lot with UFOs, and it's true already with things like Venus, phosphine, and searching for astrological signals. We have to guard against this all the way through, from however we're looking for life, however we're looking for whatever this big question is. There is a part of us, I think, I would love there to be life in the universe. I hope there is life in the universe, but I'm somewhat been on record several times as being fairly firm about trying to remain consciously agnostic about that question. I don't want to make up my mind about what the answer is before I've collected evidence to inform that decision. That's how science should work. If I already know what the answer is, then what am I doing? That's not a scientific experiment anymore. You've already decided. So what are you trying to learn? What's the point of doing the experiment if you already know what the answer is? There's no point.
It's so complicated because, so if I'm being honest with myself, when I imagine the universe, so first thing I imagine about our world is that we humans, and me certainly as one particular human, know my first assumption is I know almost nothing about how anything works. So first of all, that actually applies for things that humans do, though, like quantum mechanics, and all the things that there's different expertises that I just have not dedicated to. So even that's like, but if you take all of knowledge as human civilization, we know almost nothing. That's kind of an assumption I have, because it seems like we keep discovering mysteries, and it seems like human history is defined by moments when we said, okay, we pretty much figured it all out, and you realize a century later, when you said that, you didn't figure out anything. Okay, so that's like a starting point. The second thing I have is I feel like the entirety of the universe is just filled with alien civilizations. It's statistically, there's the important thing that enables that belief for me is that they don't have to be human-like. It can be anything. And it's just the fact that life exists and just seeing where life is on Earth, that it just finds a way. It finds a way in so many different complicated environments. It finds a way. Whatever that force is, that same force has to find a way elsewhere also. But then if I'm also being honest, I don't know how many hours in the day I spend seriously considering the possibility that we're alone. I don't know when my heart is and mind are filled with wonder, I think about all the different life that's out there. But to really imagine that we're alone, like really imagine all the vastness that's out there, we're alone, like imagine bacteria.
I would say you don't have to believe that we are alone. That you have to admit it's a possibility of our ignorance of the universe so far. You can have a belief about something in absence of evidence. Carl Sagan famously described that as the definition of faith. If you believe something with no evidence, you have faith that there's life in the universe. But you can't demonstrate, you can't prove that claim, you can't show me evidence of that.
But is there some mathematical method? Is there a way physicists think like intuition? There's some basic reason. Is there some value to that?
Well, I think you can certainly make a very good argument that you kind of already made one. Just the vastness of the universe is the default argument people often turn to. That surely there should be others out there. It's hard to imagine. There are of order of 10 to the 22 stars in our observable universe. And so really the question comes down to what's the probability of one of those 10 to 22 planets, let's say, Earth-like planets, Earth-like planets, going on to form life spontaneously. That's the process of abiogenesis, the spontaneous emergence of life.
Also, the word spontaneous.
Well, again, maybe we won't use spontaneous, but not being, let's say, seeded by some civilizations or something like that. But it naturally emerges.
Because even the word spontaneous makes it seem less likely.
Yeah.
Like this chemistry and extremely random process.
Right, it could be a very gradual process over millions of years of growing complexity in chemical networks.
Maybe there's a force in the universe that pushes it towards interesting complexity, popular complexity, that ultimately creates something like life which we can't possibly define yet. And sometimes it manifests itself into something that looks like humans. It can be a totally different kind of computational information processing system that we're too daunting to visualize.
Yeah, I mean, it's kind of weird that complexity develops at all, right? Because it seems like the opposite to our physical intuition, training in physics of entropy, the thing that should, complexities are hard to spontaneously, well, I shouldn't say spontaneously, but hard to emerge in general. And so that's an interesting problem. I think there's been, certainly from an evolutionary perspective, you do see growing complexity. And there's a nice argument, I think it's by Gould, who shows that if you have a certain amount of complexity, it can either become less complex or more complex through computation. And the less complex things are stripping away something that was necessary potentially to their survival. And so in general, that's going to be not particularly useful in its survival, and so it's going to be detrimental to strip away a significant amount of its useful traits. Whereas if you add something, the most typical thing that you add is probably not useful at all. It's probably just doesn't really affect its survival negatively, but it needed to provide a significant benefit. But sometimes, on rare occasions, of course, it will be a benefit. And so if you have a certain level of complexity, it's hard to go back in complexity, but it's fairly easy to go forward with enough bites of the cherry. You will eventually build up in complexity, and that tends to be why we see complexity grow in certainly in an evolutionary sense, but also perhaps it's operating in chemical networks that led to the emergence of life. I guess the real problem I have with the numbers game, just to come back to that, is that we are talking about a certain probability of that occurring. It may be to go from the primordial soup, however you want to call it, the ingredients of the earth started with the organic molecules. The probability of going from that initial condition to something that was capable of Darwinian natural selection that maybe we could define as life the probability of that is maybe 1%, 1% of the time that happens, in which case you're right, the universe should be absolutely teeming with life. But it could also be 10 to the power minus 10, in which case it's 1 per galaxy, or 10 to the power of minus 100, in which case the vast majority of the universe is even do not have life within it.
Or 90%.
Or
You
90.
said 1%. You said 1%. It would be 90% if the conditions, the chemical conditions of the planet are correct, or our moon are correct.
I get that. It could be any of those numbers. And the challenge is we just have no rigorous reason to expect why 90% is any. They were talking about probability for probability. Is 90% more a priori likely than 10 to the power minus 20?
Well, the thing is, we do have an observation at one of the Earth, and it's difficult to know what to do with that, what kind of intuition you put. So on top of that, because on Earth, it seems like life finds a way. In all kinds of conditions, in all kinds of crazy conditions.
Good.
And it's able to, like, basic chemistry, you could say, maybe it takes a little bit of time to technology like mitochondria, like photosynthesis, fine. But it seems to figure it out, and like do extreme well.
Yeah, but I would say we're describing a different process. I mean, maybe I'm at fault for separating these two processes, but to me, you're describing basically natural selection, evolution at that point. Whereas I'm really describing abiogenesis, which is to me a separate, distinct process.
You limited to human science, yes, but why would it be a separate process? Why is the birth of life a separate process from the process of life? But why